Okay. Hello everybody and welcome to the lecture 5 of digital signal processing. So in this lecture we are actually talking about a very important subject of statistical signal processing. And this lecture I actually decided to dedicate to the statistical signal processing, but we will probably in the few of the coming lectures also have some parts of the statistical signal processing involved, because there are some prerequisites that we need to cover before we go deeply inside. So the statistical signal processing for itself is a completely independent course. We cannot go through the course and we have just a crash course, so it's just we need to cover some important subjects in a few hours. As you might have probably seen, we have the lectures, the video of the courses in a YouTube channel. You can subscribe and you can and it will be updated. So if there is any part of probably we will not be able to actually go through all the subjects, but we try to cover as most as we can here in the course. If we couldn't, then for the left of parts, I will create another video, a short auxiliary video, and I will add it to this subscription channel. And you can go through that in more detail, you can understand it. Also, I'm providing completely independent lecture for or maybe videos for MATLAB implementation of some of these subjects that might help you when you want to do the exercises. And for the solutions, I'm not sure if both of the tutorials have already evaluated all the solutions of your first tutorial or not. Maybe they have done already. But I actually asked them to upload the first solution for the first tutorial as soon as possible. Probably within today or tomorrow you will get the first one. For the second, probably within the next 2 days you will get it. Okay. And what is statistical signal processing? Teacher tools. So, the statistical signal processing is actually a very interesting topic, and it actually talks about the random signals. But what's the difference between the random variable and random signal, and what are the properties for the random signal we are going to cover in this lecture? So, it turns out that real signals often appear to have random fluctuations. So for a real signal like speech signal, if you record it, you can see that the signal has some kind of fluctuations like this. So, and it's a stream of data coming. For many of the signals, it's like that. It depends on the frequency components inside the signal to see how much details and how much fluctuations per unit you can see in the signal. These fluctuations are hard to actually predict it in advance. And that's the part of the signal which contains the uncertainty. So you're not able to predict it. You're not able to predict, for example, what's happening between these two time instances, T1 and T2. Why? Because of the unpredictable fluctuations of the signal. That part of the signal is actually random. And in general, signals are random. The real signals mostly are random. It rarely happens that you have a signal which is deterministic. And unfortunately, whatever we said about the digital signal processing only holds for deterministic signal by far. So it means that all the course of digital signal processing and the first lectures that we had is just applied for discriminative signal processing. If you know the signal, how the function of the signal is and how it varies with the time, for example, then you can apply all those theories. But what happens when you have real signals, which are mostly random? That's actually why we need to use a kind of tools, and these tools are the probability and statistical tools to deal with this kind of signals, random signals, and to model that kind of uncertainty that we have inside the signal in a kind of disciplined manner, in a kind of principled manner. The theory that tries to cover that, which is very powerful, is statistical signal processing. We have great books for statistical signal processing, and one of the greatest references is this book, is the Statistical Signal Processing. It has 3 or 4 volumes, I think, 4 volumes probably. And this volume number 1, is for estimation theory. It has different volumes for detection theory, for identification theory, and so on and so forth. So this book is written by Stephen McKay from Rhode Island University, and it's from 2000. Well, the originally it's been written much earlier, but I think this is from 2009. So, when we deal with the random signal, the best thing that can characterize a random signal is what? How can we characterize a random signal? What's the entity if we know that the random signal is already characterized for us? So one of these things is the probability distribution function. Probability distribution function. Which is abbreviated by PDF. If we know the PDF of a signal, f of x, for a continuous signal, for example, if we know that, we are able to know all the information related to the random signal or the random variable. In general, we start with the random variable and then we can go to the random process or random signal. So PDF is very important if you want to characterize a random value or a stochastic value. Random variable, which is generally shown by x, for example, is actually a function. Is a function. Is function from sample space to real values. Is a kind of function. So we have different types of PDFs, but what I'm trying to convey as a message to you is that not necessarily for every kind of event or every kind of experiment, which is with the outcome is actually random, we can assign a known PDF function. We have some types of PDF functions which are already characterized and we know how is the figure. For example, we have the Gaussian, the normal or the Gaussian PDF or bell-shaped PDF. And the parameters of such PDF are the variance, sigma square, and the mean. And every Gaussian or the normal PDF can be characterized completely with these two parameters. So if we know these two parameters for every Gaussian or normal random variable, the random variable is fully characterized. And this is the shape of the PDF for different values. Or for example, we have a uniform random variable. So the PDF of the uniform random variable looks like this. And we know that the area below the function is always summed up to 1. So that's why here the amplitude should be 1 over b minus a. And for example, here a gamma function. I put the gamma function here. Why? Because I wanted to show something. Gamma and the Laplace PDFs are actually used for sparse signals. They are very important for the sparse signals. And the speech signal is a kind of sparse signal. So if you want to characterize with a non-PDF, it depends on your signal, types of the signal. For the Gaussian noise, for the noise actually, the background noise, which is stationary, normally we assign the Gaussian PDF. That's why it's called the white Gaussian noise, WGN. In telecommunication, probably in the courses, you might have seen that. For the phase variation, normally you have the uniform distribution. Normally in telecommunication, you see that phase follows a uniform distribution between 0 to 2 pi or minus pi and pi in a 2 pi period. And for a speech signal, and most of the sparse signals, if they are one-dimensional, normally we assign the gamma distribution. These are the sparse distributions. And for gamma distribution, we have the shape parameter and the scale parameter, which are actually represented like this. So, but there are, I want to convey this message, there are many more examples of the signals that you're not able to assign any kind of PDF. For example, it has a PDF like this. And you cannot assign any of the non-PDF functions to such kind of PDF. This can be a PDF of a random variable, x. What we are trying to do in such cases, which actually belong to the advanced courses for the statistics and the estimation theory, is the PDF estimation. There are different ways, but one of the simplest ways, when we talk about those kind of PDFs, we say actually the parametric method of PDF estimation. So we assign a kind of PDF which is already known and it has some parameters. Sometimes you see that you have histograms. Histograms are non-parametric methods of PDF estimation. And sometimes we say that if we have multiple Gaussians summed up together, for example here, normal 1, normal 2, normal 3, and normal 4. We have 4 normal PDFs, 4 normal independent PDFs with different scales and shifts summed up together, and it can be, for example, a very good approximation of such kind of unknown PDF. That's called Gaussian mixture models. And parameters for this Gaussian mixture models, which include all of these parameters for all of these ni's. So for each ni we have a mu I and sigma I squared. And the scales of these normals like alpha i's, these are all the set of parameters we need to figure out and calculate it based on the data. And these methods, like the GMM method actually, the Gaussian mixture model, is called a semi-parametric PDF or distribution function estimation. So now we have the big picture. For a random signal, we have a PDF. The PDF characterizes the random signal completely. Some of the signals have known PDFs, like this, as a sample. We have several others. Poisson, T-Student, Fisher, and so on. For those noun PDFs, we have parameters, and the parameters should be actually estimated in some way. There are different ways of estimating the parameters. You can find these methods here in the book. Maximum likelihood method, or least square method, and, for example, maximum a posteriori method, Bayesian methods, and so on. So these are the methods mentioned in the book. We are not going through that, at least in this lecture. And there are methods approximate an unknown PDF. If we have an unknown PDF, we can approximate it very good with Gaussian mixtures. So mixtures of the Gaussians or the normals. Yes, please.
How do you know your approximation is correct if you don't know the PDF?
That's a good question. We don't know the PDF, but we have the data. So we need to take samples from the Gaussian mixture. And then to try to minimize those samples taken from that Gaussian mixture, compare it with the samples that we get as a test sample, the sample comment. We take the samples thousands of times and then try to minimize the error. By minimizing the error, we try to actually get the best approximation. And that's an approximation. Don't forget about that. That's just an approximation. So there are many, many theories actually involved in how to estimate a PDF. It's also another course. But we don't want to go through that. It's just a PDF estimation. Just a general topic if you want to go to the Google. It's a PDF estimation methods. Parametric, non-parametric, and semi-parametric. That's all. So, what is a random variable? You might have known that because probably you have already you have passed the course of probability and probability theory and statistics. Such course in undergraduate. It's an undergraduate course. So random variable, as it's mentioned in Stanford University Sam Savage, is a number that we don't know yet. There are different types. We have discrete random variables. We have continuous random variables. For example, when you are dealing with a coin toss, that's a discrete form. But when you're dealing with a temperature or speech signal, these are examples of continuous random variables. So we have CDF and we have PDF, and you might have known that a PDF is actually the derivation of the derivative of the first derivative of the CDF, or commutative distribution function. And these are all the subjects related to random variables. So generally, we're not able to get the PDF of a signal. It's really hard to get the PDF of a random variable. Because the PDF essentially includes infinite number of statistics. What are those statistics? For example, mean value or the expected value. So it's an expectation of a random variable. x. What does this expectation means? It means that you actually try an experiment over and over again, thousands of times. For example, there is a bin, there's a bucket, and there are several numbers inside, or I don't know, several balls with different colors. And you just randomly choose one of the balls from that bucket. You take it out and then put it back. And you do this experiment thousands of times. What is the value as an average coming out is called the expectation value for this kind of experiment. So for a random variable, it means that if this random variable is as a result of a kind of experiment, a random experiment, then if we do this experiment for thousands of times, what is on average the outcome of that experiment? It's called the mean value. So it's also denoted by mu. Another statistics is variance. So the variance, what does it mean? For those experiments I mentioned already, so it's a kind of you want to know the energy of or the square value of the outcomes with respect to the mean. So as a good example, if you have a Gaussian signal and this is the mean value of the Gaussian, on average, what are the values or the energy of the values taken with respect to this mean value? That's called the variance. These are only two of those statistics that, collecting all of those statistics together, can characterize a PDF of a signal. And you can write down, this is just the first moment, the second moment, you can have third moment, fourth moment, and up to infinity. That's why I say that the PDF of a signal, in reality and in practice, is not possible to, in most cases, it's not possible to have it. So we have to contend to just the statistics of the signal, and normally in many cases we are just contented to the first two statistics, mean and variance. In a Gaussian PDF, mean and variance can fully characterize the Gaussian PDF. You don't need any more statistics, nothing else. You don't need it. But for every other PDF, you need actually more statistics, but it's hard to catch it. Okay, central limit theorem. What does it mean? It's a very important theory. When we were actually studying the central limit theorem in undergraduate course, we never thought that this one-page theory can be this much important. So what the central limit theorem says? It says that in a very simple statement. If we have n number of random variables combined together or added together, and they have limited variance and same mean, if this number goes to infinity, the outcome as a summation or as the combination of all of these random variables goes toward the Gaussian PDF, the normal PDF. That's very important. That's very important. Actually, one of the first solutions to the ICA problem, independent component analysis problem, which the goal in the ICA problem is to separate the signals or random processes from each other. That solution emerged from central limit theory. And the method was called non-Gaussianity, the maximum, so negative non-Gaussianity. What does it mean? It means that you have, if you can estimate a process, for example, you know that there are two sources mixed together or three sources mixed together. So what is the best estimation of these three sources is that try to get the most non-Gaussian PDF in the outputs. Why? Because if they are associated to the signal, their PDF should be in the farthest point with respect to the Gaussian. The signal has some kind of coherence inside, has some kind of information. Has, actually, let's say in the other way. When you have uncertainty about a random process and a data as a time series, when you get the samples of the data, you are getting a lot of information because you had no idea what's actually coming next. But if you have a signal or a kind of function which you know actually what it should be, or it's a kind of deterministic, then you already can guess what should be the next value. So getting the next data sample will not give you that much information. So the Gaussian PDF gives you the highest possible information. But for the other signals, so that's why the noise is actually characterized by the Gaussian PDF. Why? Because you have no idea what's the next value of the noise. Every single value of the noise is independent from its previous sample. But for the signals which come from a kind of phenomenon, it's a physical phenomenon, it's not like that. Normally we have a kind of intention, what should be the next value? We have a belief about what should be the next sample. But for the noise, we don't have any idea. That's why every sample of the noise contains a lot of information. The reason why noise is actually characterized by the Gaussian PDF is that. Now, if you want to separate the signals, you want to get a signal, you don't want to get the noise. So it means you should try to get a kind of PDF which is far away from the Gaussian. If you can make it, you will get closer to the signal. And that's the idea behind the ICA, one of the first solutions to the ICA. And central limit theorem is actually saying that you have combination of random variables, the same as combination of the signals, random signals. So when the combinations of the signals with the same PDF having limited variance and the same mean goes toward the PDF of the Gaussian. If you get far away from the Gaussian, you can separate them. So central limit theorem is a very important theory in the statistical signal processing. Here I spoke about the expectations, so the mean and the variance. You see that in both cases we need an entity which is not available, and that's the PDF. So, yes, please.
I have a question about the thing before. We're saying that the noise normally comes in a Gaussian form.
Mm-hmm.
But if we are trying to have a PDF of our signal that we don't know about and model it with Gaussians, isn't it some kind, and it has noise as well, Gaussian noise? Wouldn't it be like a lot of Gaussians in there?
I say the random signal and the random noise. The point is that for the noise, every single sample, the adjacent samples that are coming one after another, they are independent. They are assumed independent in theory, and in practice, if you try to figure out how much dependent they are, probably you will get a value very close to zero. That's why they are characterized by the Gaussian PDF. For the signal, I'm not trying to say that the signal is deterministic and you can know what is the signal. But there are information in the signal which can be somehow, you can have a kind of idea what, for example, for the speech signal, you know that based on the languages and based on the physical properties of the vocal tract and the entire organism that produces a speech, it's not possible to have two different phonemes which are completely uncorrelated, or you're not able to change the frequency rapidly because it's a physical organ that is producing the signal. This kind of information, this kind of known things about the physics is something that reduces the uncertainty. So if we say that the speech signal is random, and on the other hand we say about the belief about the deterministic part of the signal, it means that it's deterministic if you compare it to the Gaussian noise, but in general it's random. So did you get the meaning?
I think so.
So every signal, I will talk about the WOLD decomposition theory, and then you will see what exactly I mean. It has already been formulated in mathematics, and it's called the WOLD decomposition. I'll just in a few next lectures, I'll come back to that, and you will see what exactly I mean. But the noise, when I say it's the stationary noise in the environment, for example, here in the environment we have a background noise. This background noise, if you want to characterize it, the best PDF you can assign is the Gaussian PDF. But if you want to go, for example, to find a kind of Gaussian mixture for the noise, it's also possible, and you will probably get for example, 1, 2, or at most 3 Gaussians mixed together. But for a signal, for sure, you need to have more number of the Gaussians mixed together. Okay? So here for the expectations. So we want to get the statistics of a signal. We don't want to resort to the PDF because PDF is not available. We say that, okay, we are just contented to the first 2 statistics, and that's the mean and the variance. But when you want to calculate the mean and variance, you need the PDF again. It's the story of chicken and egg. So what should we do? In practice, we are using the sample mean and the sample variance. Not the exact mean and the exact variance. So in practice, what we do in our projects, for example, dealing with the speech signal or whatever signal, we try to use the sample mean and sample statistics, actually. So the theory behind behind that is the law of large numbers. It says that if one draws independent samples, you have independent samples taken from the mass of population of the data with a value with a mean called mu, unknown, but we know that it has a mean like mu and the variance like sigma square. Then as the number of observation increase, if we, for example, can have infinite number of the data samples, then we can say that with a very good approximation, the mean value is just the average over the data samples. If you can have n, which n goes to the infinity, in the limit, that's completely true. Otherwise, if n doesn't go to infinity, as a sample mean, it should be a good approximation. And it's normally denoted by m hat. And for the sample variance, instead of that expectation of the PDF, we normally use this summation. And I can say that this is somehow the foundation of the Monte Carlo methods. Using the sampling theory, the sampling or the law of large numbers is something that was, the Monte Carlo theory from one perspective can be emerged from this idea. Okay. Before going to the sample covariance or autocovariance, I need to explain about the process. What is the difference between random process and the random signal, actually? So, what is the random process? In a very simple statement, random process is a random variable varies in time. So let me explain it maybe with an example. Assume that we have a device which generates random signal. We start from today 8 a.m. to 8 p.m. for 12 hours. And we get, this is the random signal generator, for example, in a laboratory, electronics laboratory. We get the signal for 12 hours. This is 12 hours period. And we get the signal, for example, the stream of data is like this. Then we switch off this device and we switch it on again the next day, and we actually start exactly from 8 a.m., 8 p.m. We get the signals. There is something else. And we do that for n number of the times. So this is the experiment number 1, and this is the experiment, for example, number n. These are all random signals for a certain amount of time. So if you try to get the values of the signal at a specific time, for example, this specific time should be here, t1. And you get the values of the signal for all these outcomes, that will create a random variable x1. Then you go to T2 and you again get the values of the signal, and this gives you x2. These are random variables. So this is the first random variable, the second random variable. You can have infinite number of the random variables from time 0 to time 12. This is called a process. So the general picture is called the process, which shows the evolution of random variables over time. These are called ensemble random variables. And the values of the signal for each experiment are called time random variables. So when I say the ensemble variables and I say the time variables, now you have a kind of intuition. And the general picture is called the process, the random process. So what is the difference between the random variable and the random process can be shown by this example. So the random process or a stochastic process is a random variable that changes over time, or a sequence of numbers that you don't know. Maybe the second statement is not conveying any messages. Okay. There are some terminology associated to the random processes. We need to know those terminologies, and I'll try to explain them in very simple statements just using this example. What is a stationary process? A stationary process is a process which the statistics of this random variable is the same as the statistics of this random variable and any random variables over time for the process. If the process has this property that taking any of these random variables from that process doesn't change the statistics, I mean the random variable here, for example, it has mean, variance, and so on. If the mean, variance, and the higher order statistics of this variable, and this variable, and this variable, and every other variable are the same, that process is called a stationary process. White sense stationary, or WSS, is a process with just the first two statistics doesn't change. So if just mean and variance of this variable equals to this variable and any other variable, then it's called WSS process, or white sense stationary. So it's actually a relaxed form of the previous one.
One small question. An example of stationary process would be, for example, if you have a sine function but the amplitude is random, the points in which the sine actually is 0, that would be the stationary points, would it?
You mean the first one or the second?
The first one.
The first one. Okay, you have a sine function.
Yeah, and the random part is the amplitude. But
The amplitude is random. Okay.
so the points in which the sine is 0, they would be stationary because it's always going to be the same points.
I think so. But you can just, you can just take a piece of paper and write down the statistics if you can. I mean, if it's possible for the process that you define, just go to the paper and try to figure out what's the mean and what's the variance. And if they are not dependent on time, they are not dependent on time, then the process is stationary. But you can just go through the first and second. For the higher orders, it might be very difficult to calculate it. So normally in practice, we can just try to study whether the signal has White-Sesson stationary property or not. But for the higher order, stationarity is hard to catch it. So you can write down on paper the mean and the variance. If you can get the outcome without any parameter of time, it means that it's White-Sesson stationary. That's perfectly we can say. But whether it's stationary or not, we don't know, because you have to go to the higher order. Okay. And what is the ergodic? Ergodic process is the process which, for example, we say mean ergodic. Mean ergodic is the process which mean of this ensemble random variable equals the mean of time random variable. Did you get it? So we call a process mean ergodic when the mean of ensemble variable and the mean of time variable are the same. Then it's called ergodic. So we can have ergodic White-Sesson stationary process. Did you get it? Any questions? It might be a bit hard to catch in the first lecture for those who didn't have a background of mathematics or probability, but just looking at this simple example and reviewing it, I think, would be very helpful. Okay, I tried to explain about the random process in very simple statements. And mostly we're dealing with the stationary processes. But we have so many signals in nature which are non-stationary. When we say non-stationary, it means that the statistics of the signals vary over time. And those signals are really hard to catch them, to somehow predict them. But when we have stationary signals, then there are lots of good theories that we can go through. And one of these theories, the one I'm trying to actually